Okay, thank you so much. So good afternoon once again. We've already had a prayer, so we shall not take a lot more time. So we can begin. Hmm. Hmm. So, okay, Mr. Pio.
Yes, Mr. Jim.
Okay, I'm trying to share, but Mr. Pio, if you have it, you can share so that we save time.
Okay.
The document.
The document,
Yes.
let me share.
Okay. As we are waiting for the sharing, we can continue. We are looking at cells, and so far we had looked at I think you had looked at the introduction, not so? Can someone remind me where we stopped in cells? Huh. I don't know whoever is disorganizing.
Recording in progress.
Okay. Yes, Mr. Pio, thank you so much.
You're welcome.
Okay, so friends, we are still looking at those who are disorganizing us, please stop. We are looking at cells, and we are looking at the introduction of current electricity, which is cells, not so? Okay. I think we stopped at simple cells. Mr. Pio, you can scroll. We stopped at simple cells. Or we can begin with electric cells. Electric cells, then we can progress. In electric cells.
Okay. Is there a possibility of stopping those ones that are writing, that are using the pen for writing on? the notes. Friends, good afternoon. Those ones that are interrupting, we just request you that at least we shall give you time to explain something. Then you can use that pencil that you have and you write something. But as per now, we request you that just let us be patient and let us not interrupt, inconvenience others. It is just a request. Now, before we go to simple cells, let us just have a review, because we have seen others are saying that they didn't attend the other lesson the other time. Let us just have a recap of everything, then we shall look at the other one, just recapping. Now, when you're dealing with this, when we are dealing with, if we start from the cells directly, where we deal with electric potential difference, firstly, when we are dealing with electric potential, we deal with energy and the charges, whereby when we talk about energy, that is still work. And we obtain it by just, when you have the work done, divide by the charge moved, you'll be able to get electric potential. And we abbreviate electric potential as V. So that's why when we are defining it, when you're to define an electric potential, we say that it's a work done to move a charge from one point to another in a region of electric field. That's the way we define it. Like in these notes that I've just said that to move a charge from one point to another region of an electric field, and the work has to be done. So if you want to define electric potential, we say is the work done to move a charge from one point to another in the region of where the electric fields. So when you have your electric potential difference V, and you have your work done that we can abbreviate as maybe W over the charge, because now you're going to have that work done, that energy which was already done, that you're going to move, that work done, you're going to move a charge from one point to another, but within the region of the electric field. That's why we have that. So whenever you just, our electric potential, we just get from this formula that we have at this point. That you can, those that are also writing, we just request you to be just patient. We shall allow you also to record something that you may need. So that's all about when you're defining it. And you find that the SI unit of electric potential is a volt, because when you have the work done, whereby that volt is the work done in moving one coulomb of charge from one point to another. Members that are disorganizing, we just request you to be patient. So I know you covered it the other time when teacher Doreen was teaching, she explained this. So we are just recapping this, but when we reach where we are going to be slow. So when you look at this, when I define it, you want to define the potential difference. The potential difference, now when you come to the potential difference, because these are the definition, whenever you're dealing with electricity, you need to first understand the definition, the key definitions that introduce the topic. The key definition and their SI units. Now, when you talk about the potential difference, you find that these are different between 2 points in electric field, or just a difference between 2 points in the circuit, whereby you find that the work done in moving one coulomb of charge from one point to another. So you find that when we are dealing with potential difference, we say that this is a difference between 2 points in, or we can say that this is the work done in moving one column of charge from one point to another between the 2 points in the electric field. Normally, we find people confusing the potential difference and the electric field when they are defining them. This one, we start with it also, okay. Potential difference.
Just a minute.
Yes, Mr.
A minute, yeah. So I'm removing Miro so that others can learn. In fact, let me remove and report so that another time for you to join, you'll have to go through a process. Yes, teacher, you can continue.
Okay, thank you so much. Let me wrap this. So, where I was saying that people confuse electric potential and the potential difference when they are defining it. So you need to note the two differences when you're defining the potential difference and the electric potential. They are not the same, they are different. So when you're defining them, you need to understand. Now, when you look at the electric cells here. Now, when you're dealing with electric cells, I know teacher told you there are two types of cells. We have the primary cells and the secondary cells. Now, these electric cells, the work of these electric cells, they produce electricity by the chemical action. When you talk about the chemical action, their electricity, their light, that the energy they produce, it is through some chemical action that they undergo first of all, which means we are going to convert, we shall have the chemical energy. When you have the chemical energy, when I have the chemical energy on these things, I can convert the chemical energy into electric energy, which means this point, when you are dealing with these potential cells, you find that all electric cells, you find that we have the chemical energy being converted into electric energy. That's why you'll be in position to get light. That's why we shall be able to produce electricity at that point through that in conversion. So now we have the two types of cells, so these electric cells. We have the primary cells, whereby the primary cells, for them, they produce current as a result of irreversible chemical reaction. For example, when I have a battery, those dry cells that you use in the torches, if once that battery gets used up, that dry cell gets used up, you cannot charge it, you can't reverse it anymore. That one qualifies to be the primary cell. Any cell that you use after you using it, so long as it has expired, that its energy is done, you cannot go back to charge it. That's what we call the primary cells. That's why we have the simple cells. As an example, we have the dry cells. Then we have the large wet cells. Those three examples that we have, so long as they are irreversible, their chemical reaction is irreversible, those ones qualify to be the primary cells. That's why we say that the cell that produces current as a result of an irreversible reaction. When you talk about as a result of irreversible reaction, it means they cannot be recharged when it runs down at that point. Those are the primary cells. But now when you look at the secondary cells, those are cells that produce electric current as the result of reversible chemical reaction now at that point. Now, when you talk about the reversible chemical, for example, look at your phone. You can use the phone after that battery getting used up. You find that you can again charge it back such that it can produce again the current. at that point. So now mostly when you're dealing with secondary cells, the examples that we have in them, we have the lead accumulators, because for lead accumulators, once the energy gets used up at that point, you can just go and plug it, you recharge it. After recharging, you can again start using it again. So the examples of secondary cells, we have the lead accumulators, lead acid accumulators, we have the alkaline cells. We shall look at them all briefly and their diagrams, how they look like. Where when talk about the alkaline cells, where we have the nickel ion cells now at that point. So for them, when you're defining, it is just very simple. Secondary cells, you just say that is a cell that produces currents as a result of reversible chemical reaction. Or you can say that they produce current as a result of recharging when it's battery or when it runs down by passing current backwards through it. That one you had looked with Madam Doreen. So now where today we want to start with the simple cells is where our lesson can start from. Now, when you talk about the simple cell, now, if you've already studied in chemistry, electrolysis, mostly this topic is normally related to chemistry when you're studying electrolysis in chemistry. This simple cell is made up of electrolytes. When you talk about the electrolytes, is where we have the copper plates and the zinc plates. So the copper rod and the zinc rod, whereby the copper plates are positively charged and the zinc plates are negatively charged. So which means that the copper plate has a positive electrolyte and the zinc rod is the one having the negative electrolyte. Now, when you're dealing with this cell, you're going to have the zinc rod and the copper rod. After having them, you're going to dip them into a dilute sulfuric acid, not concentrated. We use the dilute sulfuric acid. The work of dilute sulfuric acid is working as an electrolyte. Now, when you dip those rods into dilute sulfuric acid, then we are going to connect it in the piece of the conducting wire, such that when you connect it into the conducting wire, at that point, we want to see that they can be able to produce current now at that point. But now, in chemistry, you dealt senior 2, you looked at reactivity series. There are metals that are more reactive and there are metals that are less reactive to that point. Now, we find that, first of all, when you look at copper and zinc, we need to identify among copper and zinc, because all of them are metals, which one is more reactive than the other in the reactivity series. You find that the zinc rod or the zinc plate first of all, it forms the cathode because the zinc is negatively charged. Then the copper forms the anode, which means when I'm dealing with this, first of all, when you are dealing with this, if I have the dilute sulfuric acid, it is dilute, we call it aqueous. When I ionize this dilute sulfuric acid, I'm going to get the hydrogen ions, 2+, it is having a charge 2+, aqueous, plus the sulfate ions. In this thing, the sulfate ions, there are 2 minus. is what we are having at that point. Now it means, but now when you look at here, the hydrogen ions have, when you look at it here, they have a 2, so we put a 2 here for hydrogen. We want to balance the charges. Then the sulfate, we have now this. Now when you look at in our notes, we just needed to edit this. We just needed to edit this at this point. So first of all, when you look at this, these two, it means the sulfate ions have ionized to form 2 hydrogen ions, and the hydrogen sulfate, this sulfuric acid here, ionized to form the hydrogen ions and the sulfate ions. We are seeing those ones that are saying they are not understanding. We don't know where you're failing to understand. Those ones that are saying they are not understanding. We are saying, first of all, let me start afresh. We are saying a simple cell is made up of an electrolytes. The electrolytes, there are 2 types of electrolytes that we have. We have the positive electrolytes and no, not electrolytes, electrodes. We have the positive electrodes. We have the positive electrodes. The positive electrodes, when you talk about the positive electrodes now at this point, now this means that the positive electrodes, these ones are found at the anode. For them, they are positively charged. Then we have, which means this is where we have the copper rod. The positive electrodes are the copper rod. We are going to look at the diagram. Then we have the negative electrodes. The negative electrodes are those are negative charge. They carry the negative charges, and that's the zinc rod. Now, when we have the zinc rod and the copper rod, which means the copper rod is the one which is a positive electrode, then the zinc rod is the negative electrodes. Now, but when you have these electrodes, you're going to dip them into an electrolyte, whereby an electrolyte is that's what we call the dilute sulfuric acid now at that point. Then when you have the dilute sulfuric acid, we are going to connect, for example, when you have a diagram like this. When I have a diagram like this, then I can have I can have the electrolytes here. This is where we have dilute sulfuric acid. This is our dilute sulfuric acid at this point. Now we have said that we're having our this is now electrolyte. This sulfuric acid is our electrolyte at this point. Now we have the 2 electrodes. We have the positive electrode and the negative electrode. So if these are our copper ions that are going to be this side, then if this is the zinc ions that are at this point, which means these ones are going, these zinc ions at this point. Yeah, when you look at these zinc ions, this is our cathode that we have at this point. Because the cathode is negatively charged, then the anode will be this side. So I get these electrolytes, I dip them into an electrode where we have
Mr. Pio.
Yes. Mr.
Sorry
Jim.
for interruption. There is a diagram down, I think. We can also use it. There are some diagrams.
Yes.
We can use them after that, I think.
Okay. So when I dip this electrolytes, when I dip this copper, the copper rod and the zinc rod into this electrolyte, the dilute sulfuric acid, then I connect it with the conducting wires at that point, we find that the zinc is going to be more reactive than the copper. So zinc is going to form the cathode and the copper forms the anode at that point. Like when you look at this diagram, which we already have in these notes, let us look at this. When you look at this diagram that we have at this point, I think this one illustrates more. Now, this is where our simple cell is formed. We have the zinc electrode here, and we have the copper electrode at this point. Now, this is our zinc electrode, which has the zinc ions, and this is our copper electrode, which is having the copper 2 ions. This one has the zinc 2 ions. So all of them, these electrodes, are dipped into dilute sulfuric acid, our electrolyte that we have at this point. You find that this zinc electrode is going to ionize to form zinc 2 ions, whereby the 2 electrons are lost in it. Then at this point where this is the point where we have the cathode, when you look at this, now this is where we had the electrolyte, because all these things are dipped into the electrolyte. That's why you have the hydrogen ions and the sulfate ions at this point all here. So we have now our copper here, and we have the zinc this side here. Then these are the connecting wires. You find that these wires are connected this copper is connected from the copper rod to the zinc rod. That's where we have the wires, which means the current is going to flow into it in these connecting wires. Now, when we have them, which means from this, whenever you have this, the sulfuric acid, which is dilute, when it ionizes, we form the hydrogen ions plus now the sulfate ions now at this point, 2 minus. But now these hydrogen ions, they have, at this point, we put a 2 here, which means the sulfate ions have ionized to form the hydrogen ions and the sulfate ions at this point. That's why we have them from this diagram here. That's why we have it from at this point here. We are having it in this point. This way, that's why you have the 2 hydrogen ions, this one and this one, and our sulfate ions at this point. Which means this is an electrolyte. Now inside here is where we have the electrolytes here. So now when I connect this into this, that's why we have connected them to form this. You find that whenever these 2 things are connected, you're going to have yes, there's someone who's asking that between the cathode and which one is positive and which one is negative. The cathode is positively charged and anode is the cathode is negatively charged and anode is positively charged. So now when you look at the reactivity series, we know that zinc, when you look at zinc and copper, zinc reacts more than copper, which means zinc comes first before copper. at that point. So when I have now these electrolytes, you find that these hydrogen ions are going to form the bubbles. That's why we have now the bubbles at this point. They are now bubbling. These hydrogen ions are forming the bubbles. So when they form, so when these hydrogen ions combine with the sulfate ions, that's why we form the sulfuric acid now, all from this point here. That's why when the sulfuric acid ionized, we form these two things now at that point. Which means the work of these hydrogen ions, this is where polarization is going to take place in this. Now, let us just look at how a simple cell works. Then we can understand now at that point when we look at how a simple cell works. Because that explanation all comes from how, when we are explaining how it works now, we can now understand it from there. So, when we talk about the action of a simple cell, the first thing is you're going to find that the zinc plate, it is a metal, for it is going to dissolve slowly. And when it dissolves slowly, it forms the zinc 2 ions. But now these zinc 2 ions, you find that at this point it was a metal, which means we are going to have the 2 electrons at this point, such that when these 2 electrons react with this zinc 2 ions, it's going to become still a metal, goes back to the metal. But now, these zinc ions that we are having from this point will be displaced by the hydrogen ions to form the zinc sulfate. So now we shall have the zinc 2 ions being displaced by the hydrogen ions, where we have now this. So now when these zinc ions react with the sulfate ions, we form the zinc sulfate now. All of them have the oxidation state of, this zinc has oxidation state of 2, sulfate also has the oxidation state 2. So we have now this. Now, at that point, others are saying they are not seeing. So, when you look at this, that's why when we look at this, let me rub this. Now, those ones that have questions, you may, Mr. John, there are those ones that have questions. They may raise up their hands and we allow them to first ask.
Okay, but meanwhile, let me attend to those who are writing in the chat, yeah?
Okay.
So that we save time.
It is fine. Thank you so much. We shall share the notes on the platform. You don't mind, you just listen. Then we shall share these notes on the platform and you'll be able to write it. So long as you understand what we're explaining from here, the notes will be shared to you and you will write from there. Because when we allow you to write from here, it might take much time. So, which means this, when you talk about, whenever we are dealing with this simple cell, we have said the zinc plate, which means when you talk about the zinc plate, the zinc rod, the metal, it's going to start dissolving slowly. Into that solution, the solution is where we have our electrolyte, the dilute sulfuric acid. So the zinc plate dissolves slowly into the solution to form the zinc ions, whereby those zinc ions are going to they are going to displace the hydrogen ions to form the zinc sulfate. That's why you have this at this point. Because first of all, the zinc, the metal our zinc, first of all, dissolved in the solution to form this. So then this zinc 2 ions display, they remove the hydrogen ions, so then they react with the sulfate ions to form the zinc sulfate at that point. Now, after forming the zinc sulfate, what happens to the displaced hydrogen ions? Now, the work of the displaced hydrogen ions are going to move to the copper. For them, they are going to move to the copper plate at this point here. When you look at from this diagram here, when we are in this zinc, the zinc is going to displace, first of all, the zinc, the metal is going to first ionize to form the zinc 2 ions. Then those zinc 2 ions displace the hydrogen ions. They remove the hydrogen ions. Then they remain with the sulfate ions. They react with the sulfate ions to form the zinc sulfate. Then now the hydrogen ions, these ones, that's why you see that these hydrogen ions have moved to the copper plate now at this point. This is where they have moved now. These hydrogen ions have moved to the copper plate. So now when they have moved to the copper plate, at that point, you find that the electrons from the zinc is going to travel into the circuit. When they are moved, these electrons from the zinc plate, they are going to move into the circuit. At this point, when they move into the circuit, you find that they are now reaching to the copper plate, now this side. Now, when they reach, we want to see where will happen to the hydrogen ions, which were being displaced now at that point. Now, which means when the electrons from the zinc move to the copper plate, you find that whenever they reach to where we have our copper plate or the copper electrode, at that point, you find that the hydrogen ions are going to combine. First of all, these hydrogen ions that we are having now at this point, that way first of all displaced these hydrogen ions first. They are going to combine with these electrons, then we form a gas first. Hydrogen gas is going to be formed at this point. Then we have a 2 here. Now, what happens when they form a gas? What happens to this displaced hydrogen ions after forming now a gas at this point? You find that when the gas is formed at this point, you find that those electrons, now, this is where now we are going, the electrons are going to move from the anode, from the cathode to the anode. Then first of all, which is going to cause the flow of electricity, which means from the anode to the cathode, from the anode to the cathode they are going to displace. It's going to deflect at that point. Now it's like this. Let me first wrap this. Now, this gas that we have from here, remember the electrons were now flowing, they all went to the copper plate. Now, when the electrons went to the copper plate, you find that those electrons are flowing from the cathode to the anode, because where we had our cathode was this point. We had our cathode here, we had the anode here. Now this is the flow of electrons, which means they are flowing from the cathode to the anode now at this point. So where our zinc is here, our cathode. Then we have our anode at this point where we have the zinc. The zinc is our anode, the copper is our cathode. Then the electrons are flowing at this point. So when the electrons are flowing, now that's where our current is formed now at that point, because now they are connected, the electrons have started flowing at that point. That's why we're able to form that. Then now you find that those electrons that were flowing from the cathode, like here you're seeing the cathode already from here to the anode. This is the flow of electrons, this direction where we have this E. This is the flow of electrons. Now we have the electrons are flowing from this anode to the cathode. As forming these ones are going to deflect at this point. That's where our current can be formed at that point. So that is how a simple cell works. You deal with the cathode and anode, and we have the two electrodes, the zinc electrode and the copper electrode. Then all of them, we have one electrolyte, which is dilute sulfuric acid. When all of them are dipped into them, then now you first explain that the zinc metal ionizes form the zinc 2 ions, whereby the zinc 2 ions display the hydrogen ions to form zinc sulfate. Then you write this equation. After forming, you find that the displaced hydrogen ions move to the copper plate. Now, then you find that that zinc is going to move through the circuit and they reach the copper plate. Now the zinc also moves through it and reach the copper plates. Then the electrons from the zinc plate is going to travel through that circuit and they also reach the copper plate or the copper electrode. Now when they reach there, those electrons are going to combine with the hydrogen ions to form the hydrogen gas. That's why we have this hydrogen gas at this point.
Let me first allow some questions as if they have some burning questions.
Yes.
Some are asking which one is cathode, which one is positive, cathode or anode. But just first allow some questions. Let me see if we can allow some people to ask some questions. Let's Bridget, are you able to ask now? Or alternatively, we can have, you can send Amara Mowes. She's a co-host. I don't know whether she's a teacher or a student. She can ask on behalf of others because her microphone is unmuted.
Teacher, good afternoon.
Good afternoon to you.
I'm the co-host, but I can assist if you need to, and select people who want to ask or help with the chat if you want to.
It is fine. Those ones that want to ask, they may raise up the hand that have burning questions, then you allow.
Okay, because there are some people right now who have put up their hands. Can I pick two people and you answer their questions?
Yes, you may.
Okay. Brooke Jones, please unmute. Bridget Jones, sorry, please unmute. Bridget. This person. Patricia, please unmute.
Thank you.
You're welcome.
Good afternoon.
Good afternoon.
Okay, sir. I'd like you to please elaborate on the part of the anode and the cathode. Is the anode the negative, or it's the cathode? And then
Yes.
the anode is the negative one.
Yes.
So which one carries positive charges between the zinc and copper?
Now, when you look at this, we know the anode is negatively charged and the cathode is positively charged. And the electrons move from the cathode to the anode at that point. So when you look at, first of all, when you look at the zinc is positively charged first. That's why, first of all, when you look at the zinc metal, when it ionizes after, the zinc metal ionizes to form the zinc 2 ions, whereby you find at that point, the electrons were lost. That's why we are adding +2 electrons, because the zinc metal loses the electrons when it ionized. Then it forms the zinc 2 ions. Then we add those 2 electrons that it lost, because when you add those electrons, then at that point you find that it comes back to the zinc plate. But
Okay,
now,
sir.
yes.
Okay, basing on this diagram on the right, I see the flow of electrons from the anode to the cathode, and I noticed that there's more like zinc is the one carrying the negative charges to the copper. Is it okay? Yeah. Is it like that? Should I ignore the fact that the anode, the anode has its own task, even the cathode, but then the fact that the zinc is having the negative charge and it's the one carrying it to the copper. Okay, it shows like zinc is the one carrying the negative charges and then copper carrying the positive ones.
You see, zinc is carrying the negative charges because zinc is more reactive than copper. You get in the reactivity series.
Yes.
So the one which is more reactive reacts faster than the other one. So we consider the one which is more reactive. So now, the reason being, zinc being more reactive, now at this point, it carries the negative charges.
Okay.
At this side, because it's more reactive. Then the electrons are going to move from the anode going to the cathode. You get?
Yes.
Mm.
Okay, thank you.
You're welcome.
Me, sir.
Yes.
Okay, my question is about, okay, what you're trying to say is that the zinc, since it's more reactive in the reactivity series, so it also comes out that it takes the negative, is it electrode? And then copper, being less reactive, it takes the positive.
Yes, you see, copper being less reactive might not be in position to displace the hydrogen ions faster. So we look at the one which is more reactive is the one that displaces the hydrogen ions faster. When they displace, then they are going to react with the sulfate ions now at that point. So if copper was more reactive than zinc, we could take copper. So, but you look at the two, when you're picking the electrons, when we are dealing with when a simple cell, we pick 2 electrons, 2 metals. We have picked copper and zinc, but after you picking them, look at among the 2 you picked, which one is more reactive than the other. The one that we have now, the one which is more reactive, which means the one which is capable of displacing the hydrogen ions, which means hydrogen ions are positively charged. So which one can displace the hydrogen ions? So you find that the one which is zinc displaces the hydrogen ions. So if they are displacing the hydrogen ions, at that point, you find that zinc is going to carry the negative. This zinc carries now a negative electrode at this point because it can displace the hydrogen ions. Remember, hydrogen ions is positively charged now at that point. You get it? But
Yes.
But copper was less reactive, right? So we are trying to first ignore copper because it is less reactive, and we concentrate on the zinc. The zinc the zinc 2 ions or the zinc plate, we deal with the zinc plate, because at that point, when those hydrogen ions are displaced, for them, they are going to that's why for them, they are going to be displaced and they go to the copper. They are going to go to the copper plate. When they reach the copper plate, that is where they are going now, the electrons, the hydrogen ions are going now to combine with the electrons, then they form the hydrogen gas at that point. You get?
Yes.
Then now you find that the electrons are moving from the anode going to the cathode. We have you seen us? We have not carried any ionization where copper has ionized to form the copper 2 ions. No, it is only the displaced hydrogen ions that you will have at this point. When these hydrogen ions are displaced, they come this side. When they come from this side, that's why you have this we have these electrons combining with hydrogen ions displaced to form the hydrogen gas, which is this. You get?
Yes,
Which
thank
means these hydrogen ions have undergone reduction, then the zinc undergone oxidation. You get?
Yeah.
Because oxidation is the loss of the electrons. Then the reduction is where we have the gain of the electrons. Electrons are gained now at that point. So this one, we lost the electrons here. Here we are gaining the electrons now from this side. Here we are losing them.
Okay.
Yes. Okay, we may continue if there are no more questions. So, that's why we have that, a simple cell. That's why you find that when our electrons flow like that, then now you find that the electricity flows from the anode to the cathode. So you find that now, then that's why you find your voltmeter deflecting now at that point. Now, well, let's look at the defects of a simple cell. Now, a simple cell, when you look at the defects of a simple cell, remember, a simple cell works for a small time. It works for a small time. When it moves for a small time, immediately the current stops flowing, it undergoes polarization now at that point. Now, it means at that point, you find that those hydrogen ions, those hydrogen ions which were collected which were collected are going to bubble within that cathode, within the anode. When they bubble from there, you find that the hydrogen ions from there are going to be insulated partially from our electrolytes. When they're insulated partially from the electrolytes, they are going now to slow the working. They reduce the working of that cell. When it reduces the working of the cell, you find that the cell is going to stop working slowly until the cell stops working completely. Those are not like just the defects of the simple cell. Like what happens in the simple cell when look at, but now we look at how can we prevent such a defect? Like when you have your dry cell, then with your dry cell, remember when it gets used up at that point, you find that they have something which is like an alkaline that can start which is going to be produced at that point. One to say how can we stop, how can we prevent such? Like when you look at a dry cell, the time can reach find that when you look at that metallic thing, this thing here, when you have a dry cell, it is not here. I don't know. Let me check whether this diagram. When you look at this dry cell at this point, you find that in this brass cap here, it is going to be, whenever you try to connect a wire as if it is not reactive. It's that whenever wire is connected to it, it is like it is insulated. It is not able to allow electrons the current to flow through it. So one to say, how can we prevent such a thing now at that point? The first thing is, we have the thing, you need to brush it. That's why we have now here that how do we prevent the defects in the simple cell? That's why we have that by brushing of the anode. You keep on brushing the anode occasionally. Then if that thing undergone polarization, it means we need to depolarize it. We need to depolarize them using certain things. So certain, like we can use potassium dichromate or manganese dioxide. So you can again prevent it by depolarizing them using potassium dichromate or manganese dioxide. That also, which means at that point, it will make it at that point, that chemical that you're using for depolarizing is going to react with hydrogen. When it reacts with hydrogen, then that's why it can be portioned to form water now at that point. That's why we use manganese dioxide, or you use potassium dichromate at that point. Those are the ways we can prevent those defects. Then, now this is what the local action. The other one, how a simple cell works. Now, a local action. Now, in the laboratory, you can just go to the laboratory and produce your own current from the laboratory. How? Now, when you go to the laboratory, you can just produce current by you can pick certain metals and the wire, and you connect, you find that current and electricity can be generated just from when you go to the laboratory, you can generate it by just going to pick certain reagents in the laboratory, and when you connect them, then you find that when they combine, at that point they react and you've been positioned to form current now at that point. So when we talk about the local action, the local action is, which just means, in simple terms, it means just the warning out or the wiring down of the cathode, where we have now our zinc electrode. Because now that thing, because of the impurities that we are having, that reacted with acid, then they formed the hydrogen bubbles. Because that cathode had the impurities reacting with the acid when they were forming, then when they're reacting with acid and they form the hydrogen bubbles. That's all about the local action. So that's why we have it from here, that is the wearing up or the wearing down of the zinc electrode as a result of the impurities on place reacting with the acid to form these hydrogen bubbles now at that point. Then, how can you prevent that local action, that when the zinc electrodes are worn out, how can we prevent the worning out of them? Which means the first thing is you need to keep on cleaning the zinc plate. But when you're cleaning it, what do you use for cleaning it? Some people make a mistake. You need to use an acid. We use mostly, you remember, concentrated salvic acid. That's the one we use, because when you get concentrated salvic acid, when it's concentrated and just pour it down, maybe on the cement, you're going to see the way it's reacting faster, and it can even burn you. So you clean the zinc sulfate using concentrated sulfuric acid. Then after you cleaning it, you get now mercury and rub it such that it can avoid burning out. It can avoid burning you out. Now, you find that mercury that you've used is going to cover up all those impurities. When it cover up the impurities, at that point, they are going to prevent your zinc electrode from being in contact with the acid electrolytes now at that point. That's the work of that mercury that we have. That is all about the local action and how you can prevent the local action now at that point. As far as the simple cell is concerned. So we may, in case there is anyone with a question, we may allow one. If it's not there, we may now go to the dry cell.
Excuse me, teacher. Sorry for the interruption, but there is one person who wants, there's a hand here. They want to ask a question.
Yes.
Olivia, can you please unmute? Olivia.
Okay, thank you, sir. Good afternoon.
Good afternoon.
Good afternoon.
My question is, you said that the cathode is always a negative and the anode is always a positive, if I'm not mistaken. But you said that zinc electrode is a negative, so is a cathode, and a copper electrode is positive, and so is the cathode. So on the other diagram, I saw zinc electrode as anode and copper electrode as a cathode. So according to this statement on local action, is saying that it's the gradual wearing down of the zinc electrode into bracket cathode. So now I'm confused. Zinc electrode and copper electrode, which one is a cathode and which one is anode?
Thank you so much. We have said when look at the anode is negatively charged, then the cathode is positively charged. Now, zinc plate undergoes oxidation, which means if it undergoes oxidation, it loses the electrons. Now, when you are in the other side of the copper plate, that is where we had, because the hydrogen ions were displaced to the other side, that's where we find the reduction, where reduction means the gain of electrons. Electrons were gained from the other side. It means the anode is negatively charged and the cathode is positively charged. So, at that point, it means whenever when looked at this diagram, yes, at this point, are you seeing this copper is positively charged? And this is here where we have the negatively charged. So which means we have our anode this side, we had our cathode this side. Now, what people normally confuse is there is a difference between flow of electrons and the flow of current. That where do electrons flow from up to where, and how does current flow? Those are the two things you need to differentiate. The way electrons flow is different from the way current flows. You get it? Are you understanding? Where for current, they flow from the flow of current, first of all, electrons flow from the zinc plate to the copper plate, which means the electrons flow from the anode to the cathode. Then for current, it flows from the cathode to the anode. That's the difference between two of them. So now here, when we came to the local action, we have said, no, when we talked about the zinc electrode, this should be the anode, not a cathode. I think we just need to edit this. Because when we talk about that, the global wearing down of the zinc electrode, as a result of impurities on impurities placed, reacting with acid to form the hydrogen bubbles, it was from the anode. The zinc electrode is from the anode. At that point, because all the hydrogen bubbles, you see these hydrogen bubbles, they were displaced to come this side of the copper metal. All these places here. They are formed on the copper. They are formed. This is where we have the hydrogen bubbles. Polarization took place from here. Now, on these hydrogen bubbles, where polarization has taken place from here, this is where we have the cathode. So we are just going to edit these notes before we send them to the group. Mr. John
Okay,
will
sir,
edit
thank you.
them. We are going to edit it. This one had just a mistake at that. With these notes, we shall
Okay.
edit.
Yes, true.
Then another thing,
True.
sir,
Yes. Yes.
then I'm also confused on zinc. According to what we know in the chemistry, we know that when the metals are forming iron,
Yes. We are not getting you.
Hello?
Yes, we are getting you now.
Yeah, we know that when an element loses electrons, it the ion. An element gains electrons. Yes.
We are not getting you totally. Okay, maybe let him first. We are not getting you. Maybe you first get a clear network, then we shall give you again an opportunity to ask. When you get a clear network, we shall give you an opportunity to ask. Because as if your network is not stable.
Teacher, I was inquiring. Sorry again,
yes.
Teacher. I was inquiring. Can we let someone, just one more person, to give you their final question?
Yes, you allow.
Okay. Joshua, please unmute.
Good afternoon.
Good afternoon.
I was asking, so when the current is moving in the opposite direction, the charge of the copper and the zinc changes of
zinc. There's a difference between the flow of electrons and the flow of current. Current flows. The electrons flow from the negative to the positive. That current flows from the positive to the negative. So when you looked at the diagram, when you have a diagram like this, when I have one rod here and I have another rod, this point here, if this is where I have the zinc rod and this is where I have the copper rod at this point, this one is negative, this one is positive. This is where we have our cathode. This is where we have our anode.
Mr. Pio, we can't see. Maybe you are demonstrating on a screen, but we cannot see.
None of the people is able to see.
I can see.
Oh,
Are you
okay.
seeing?
Maybe it's me. It's fine.
Now,
If they can see, it's okay.
now you find that the electrons, they are going to move from here up to this. This is a flow of electrons now at that point. Those are of electrons only, which means electrons are moving from a negative side to the positive side. But current flows from the positive to the negative. That's the difference between two of them. Now for current is going to flow from this positive coming to the negative now. So you need to differentiate them. Nothing changes that we are going to change that. Let the copper become now zinc, then the zinc becomes copper. No, they remain in their very own position. It is only the arrows that are changing. That this one moves from this up to this, then that moves up to that. Are we together?
Sir, yes,
Yes.
sir. Now,
Yes.
I thought current moves in the direction of electrons.
The current moves in the direction of the electrons.
Yeah, that's my question. Why does it change?
Now, when you look at a battery, let me rub this. Now, the work of electrons, when we look at a battery, like if this is my cell, if I have a dry cell like this, that I have my circuit as this, which is connected at that point. How does current flow in this? That's the thing we need to understand. Because whenever we have now a circuit, that you have a circuit, we deal with the flow of current only. That is what we are dealing with now at that point. How our current flows. But now, the work of the electrons, because when we have the electrons now passed over at that point, those electrons that we had at that point, those electrons were just helping us. First of all, remember we were dealing with metals at that point. Now we wanted to see how the simple cell works in when we have the metals. Now, those metals themselves being reactive, one being more reactive than the other, we can't combine all the two metals and we expect to form current at that point. Which means it is through those electrons, the flow of electrons, that whenever the electrons are going to flow and they keep on reacting with whenever they keep on reacting with the metal, with the metal, for example, for zinc, it is going to lose the electrons. Electrons are lost from zinc at that point. That's why we get the zinc 2 ions, which means then those zinc 2 ions, we're forming them in order to help us to push the hydrogen ions where there was a copper plate, such that from the copper plates, the hydrogen ions will be able to gain the electrons that were lost to form the hydrogen gas. That's where polarization takes place at that point. When polarization took place from that point, then that's the point you find that the electrons are going to move the electrons are moving from the anode to the cathode. You get it? Now, when the electrons moved, when polarization took place, now that's the time we are generating now current at that point. Then you find that now currents are going to move around that simple cell. When now that's the time the current is produced at that point. After then the voltmeter can start deflecting at that point. Then that's why you see that it is electrons first, the flow of electrons that will result into the current being formed. Then the current also, now the currents can move around the simple cell. Now at that point we have formed now the current at that point. So those things are different.
Okay, sir. Thank you.
So we look at a dry cell. A dry cell is, every one of you knows a dry cell. There are those ones that are asking questions. You may be helping. Those ones that are understood, you may be helping. Maybe those ones are joining late and be giving them some clear answers. Now, a dry cell, first of all, for it just, it is also having, a dry cell is having the rods at that point, whereby at that point, first of all, a dry cell uses just ammonium chloride. Inside it, we find ammonium chloride in that dry cell. Now, that ammonium chloride is working as an electrolyte. When ammonium chloride, that ammonium chloride is working as the other time when we are dealing with a simple cell, we use dilute sulfuric acid, which was working as an electrolyte. But in the dry cell, we use ammonium chloride as an electrolyte. Now, which means when you are dealing with the ammonium chloride, we have our ammonium chloride. So, you find that we are going to have the anode, and still we are going to have the cathode at that point. But it is the cathode will be formed. First of all, when you're dealing with it, you find that the anode is where we have the copper rod. The copper rod the anode is the copper rod that we are having at that point, whereby that copper rod can be surrounded. First of all, it is surrounded by the mixture of carbon and manganese dioxide. But all of them are placed in zinc. It can be placed in zinc. Then when you place them in zinc, they will be in position to form now the cathode at that point. So, but now, that is all what is contained in the dry cell. That the dry cell, it uses ammonium chloride as an electrolyte, whereby in that thing, the copper rod, the carbon rod is the anode. Then still, you find that our zinc is going to be the cathode. This is now a dry cell. Because we have carbon, this time we're using carbon and zinc. Now we want to see how a dry cell works at this point. For a dry cell, it has a jelly. Because when you look at that thing, it wants to look like white when you open it. When you open a dry cell, sometimes you find it producing something which is sticky, but it's like white. That's just a gel, which is that jelly now is where we have zinc and ammonium chloride. We have ammonium chloride, that's our gel that we have at that point in that dry cell. Whereby the source of energy that we have in the dry cell is we have the chemical energy in it. We have the chemical action in it, which means that chemical action occurs between zinc and ammonium chloride jelly at that point. So you find that whenever we have the ammonium chloride and we have zinc, this ammonium chloride first at that point is going, because we are going to have first of ammonium chloride, ammonium ions and chloride ions. Now, the ammonium ions will be the ones that are going to produce the hydrogen gas. When that hydrogen gas is produced, it's going to collect in the carbon rod where we have our anode. When it collects in the carbon rod, then it is going to polarize in the cell. When it polarizes, remember at this point, we had the manganese dioxide now at this point, which means we can have manganese 4 oxide now at that point. The manganese 4 oxide is going to oxidize the hydrogen ions that were produced in that cell. Then when it oxidizes the hydrogen ions which were produced in that cell, then you find that it's going to supply current. Then now at that point, those manganese ions, after now oxidizing the hydrogen ions, Because when you have now the manganese oxide with the hydrogen ions, it's all going to oxidize the hydrogen ions to form water. Now that water which is going to form, it means now at that point, is going to enable the supply of current in that cell for some small time. That's why you find that a dry cell works for a shorter time, a small time now at that point. Now, it means if we are dealing with the local action of the dry cell, these are the things you should know only. So you find that you're going to tell them that in the dry cell, the source of energy used in a dry cell is chemical energy. That's energy we form between the zinc and ammonium chloride gel. Then the hydrogen ions, which means the hydrogen ions we produce from the ammonium chloride, because ammonium chloride first ionizes from ammonium ions and the chloride ions. Then the ammonium ions are going to undergo reduction to form the hydrogen gas. When the hydrogen gas is produced, that hydrogen gas is going to go where there is the carbon rod, the anode. When it goes to the anode, when it collects at the anode at that point, then it's going to polarize in the cell. Then after it being produced, that's collected in the anode, then the manganese oxide oxidizes the hydrogen ions to form water, which is going to enable the supply of current in the cell now at that point. But for a small time, not for all, it just allows the supply of current for a small time. That's why you see that the simple cell does not work for so long. Then that's the way we can now talk about just the action of a simple cell. That's why you find that a simple cell, most simple cells, you find that it can produce an EMF of about 1.5 volts. It doesn't go beyond that. That's what a simple cell can produce, which means the simple cell can dissociate in a small period of time. It can dissociate in time. It can't, you find that this local action that we do, it cannot be stopped in the dry cell. So because a dry cell dissociates with a small time, and for it produces an EMF of about 1.5, doesn't go above that. That's why whenever you buy an NS dry cell, you check it, you find that it is written there, those big ones, you find 1.5 volts, which means that is the EMF that dry cell can produce. So if you have something which consumes much power and you find that what they want is not matching with that dry cell, you need to keep on combining more. That's why you find that whenever we are in the lab and you're using a dry cell, you find the cell holders, some of them have two, which means the bulb we are going to use, or the ammeter, for the ammeter to deflect, or the voltmeter, there is a certain voltage that ammeter needs, so that voltmeter needs to deflect. If it needs 1 point, just like around 1.5, not above 1.5, we use one dry cell. But if it's using more than that, some you find that they need a current of 2.5, 3.0. That's why you find that some cell holders, they are two, that they need two dry cells to allow such that it can be in position to deflect the voltmeter or the ammeter or the galvanometer from there. So that's what we look at that. So now when you look at the simple cell, like a dry cell, because now we want to look at the advantages of the dry cell and the simple cell when you compare two of them. The first thing is, the simple cell is portable. You can carry it, even put in your pocket and you move with it. But for a simple cell, you can't do that. Now, in a simple cell, it is electrolyte. It's in jelly form and it can't be powered. But that's a dry cell. But a simple cell, we had dilute sulfuric acid, which is just in a liquid form. It can power easily and you lose everything. That's why for it, You can form it for a simple cell, you can form it in the lab. You can go to the lab and make your own simple cell and it works from the lab. But for this one, it is electrolyte, is in jelly form and it can't be poured easily. And another advantage for it, dry cells, we use it in torches, we use it in watches, stop watches, we also know stop clocks, etc. That's why we normally use the dry cells. Those are the advantages of a dry cell compared to a simple cell. Now, this is a diagram of a dry cell, an illustration of a dry cell. Now, when you look at this illustration of a dry cell, we have this. Now, the gel we are talking about, this blacker thing that we have at this point, this is what we call the carbon rod, where the hydrogen gas which was being produced came and was collected here at this blacker thing here. The carbon rod is the carbon rod. Now, from here, this is where we have this is the positive contact here. This is a brass cap, which is a positive contact. Down here, behind it's where we have a negative contact at that point. Now, where do we have the ammonium chloride, that jelly that it has? That jelly is found just when you remove that red thing in a dry cell, when you remove that cover of the red thing, you're going to find, but no, you find that is that jelly. That's why you have the black thing here. This is why you have the ammonium chloride jelly now at this point here. That's why we have the ammonium. This white thing here that we have here after the black thing, because the black thing is this is just a zinc can here. Now this one, which is now above it, is where we have the ammonium chloride jelly now. This white thing here. Normally, you normally see that white thing, that gel on it, you normally see it after the cell dissociating, right? You've used your cell, now it has lost energy, now it is dissociating. Time is going to reach that is going to start producing that white thing. That is what they call the ammonium chloride jelly now at that point. But when the cell is still new, it is hard for you to see it. It needs when the cell dissociates, then you can be in position to see. Then that red thing is just an insulator. That outer cover for the cell is an insulator. That's why you have it here. This is an insulator. Then still there is that blue thing which covers. When you buy a cell, you have a blue thing covering as is leaving the brass cap on top. This blue thing here, that's what you call insulating top still. The blue thing in the dry cell, you have the insulating top still. If you get the dry cell, you check that blue thing, that's our insulating top cell. Then down that thing, you will have, now we what else haven't we? Now inside, what the thing which is surrounding this carbon rod, that's where we have the mixture of carbon and manganese oxide is the one which is being surrounded on this, because when it's surrounding, that manganese oxide is the one that reacts with which oxidizes the hydrogen to form water, such that it will allow the supply of current for some time. That's this thing here, which is surrounding this blacker thing. You normally see when you open a dry cell. That's what we have, the mixture of powdered carbon and manganese oxide at that point is what we have now this. Then finally we had the cardboard disc. It is ever down there. We just open, when you open now, like when you open that white thing from the negative side behind that dry cell, you're going to see the cardboard disc now at that point. Then that is all about the dry cell. If you draw it, are we together? So we shall share you the notes and you can draw it and you practice. What is the time? So
Teacher, it
Let
is
us
340.
yes. Let us wind up with this. Like this question is saying, explain why EMF of a dry cell decreases with time, even when not in use. For example, if you buy a dry cell and just bring it, put it in your room, you remove it from that paper which is covering it. If you remove it from that paper which is covering it, just allow it to stay from there. Then try to check it. You find that it is EMF has decreased. The voltage is not again 1.5. Now, it means, now I want to explain that even in some time when you buy dry cells and you leave it in the room for some time, you're going to find that when you try to test it, it is not working totally. At that point, then you say, yeah, I didn't use this dry cell, but what happened? Now that's what we want to explain, that why does that EMF reduce in time even when we are not using it? Now it means the anode, when you put it down, that's why I said that when you put those dry cells maybe on the cement, or when you just put them on the cement, it's cold now. It's going to be, the cement is very cold at that point. It means the anode will lose all the electrons. Remember, the electrons keep on flowing. So the anode is going to lose all the electrons. The electrons all have flown from the anode. They have left now at that point. What happens when the anode loses all the electrons? That electrolyte now at that point, the electrolyte that we are using now at that point, that ammonium chloride jelly, will be unable to supply anymore. It will not supply anything now at that point. Then you find that the reaction is going to keep on reducing slowly. Then you find that the EMF also is going to reduce. So the first thing is, if they ask you that explain why EMF of the dry cell decreases with time, even when not in use, it means with time, the anode loses its electrons. When the anode loses the electrons, the electrolyte, ammonium chloride jelly, will be unable to supply current anymore. Hence, the reaction reduces or slows down, and the EMF decreases or drops. That is the explanation you can give at that point, in case you're being asked. Are we together? Because, as you know, the negative electrode is the most important thing in the cell. That negative one is the one which is more dangerous. Those ones that are saying, pardon, we have said that if they say explain why EMF of the cell reduces or drops in time even when it is not used, you say that the anode now at that point loses the electrons, which makes the electrolyte, ammonium chloride jelly, to stop supplying current. Hence, the EMF decreases. You just give it in that form. EMF is electromotive force. When you talk about the EMF, then that's electromotive force. Let us wind up with the Lange wet cell. Now, this one is an example of a primary cell, because we said that the primary cell, once it gets used, you can't recharge it anymore. This is another example that we have now at that point. So it means, first of all, the Lange wet cell, it is going to use ammonium chloride solution. It's just in a liquid form as an electrolyte, the Lange wet cell. So I want you to differentiate between what does a simple cell use as an electrolyte. The simple cell, we looked at it, what it is as an electrolyte. What does a dry cell uses as an electrolyte, and what does the Lange wet cell uses as an electrolyte? You need to differentiate All of that. That's the first thing you need to differentiate those electrolytes. Now it means this large wet cell is like a dry cell. There is no difference between it. The only difference is for it uses liquid ammonium chloride solution as an electrolyte. That's the only difference between a dry cell and a large wet cell. The other one was just using ammonium chloride jelly. This one uses liquid ammonium chloride solution. That's the difference of them. But now when we are talking about how it works also, you find that it does also the carbon plate. That carbon plate, first of all, you find that the positive contact of the wet cell, the large wet cell is going to be surrounded by the carbon plate. Then it is going to depolarize with the mixture of the powdered carbon and manganese for oxide. When it's polarized at that point, you find that the zinc rod acts as the negative pole now at that point, because now that's the point when the zinc rod acts as a negative pole now at that point. So it means that the polar spot that we had at that point, first when we have the polar spot at that point and the zinc rod, if you find that the polar spot and the zinc rod are going to be placed inside the glass jar containing a solution of ammonium chloride. So if you're being asked to explain how the large wet cell works, you're just going to first say that it uses the liquid ammonium chloride solution as an electrolyte. Then it is positive cell. The positive pole, the positive contact is the carbon plate surrounded by depolarizing mixture of powdered carbon and manganese for oxide in the polar spot. Then the zinc rod acts as the negative pole. Now, which means here we have the carbon plate and the zinc plate also. Now in this wet large cell. Then for it all, it is going to have, it is in them, it is the manganese for oxide, which is also going to keep on oxidizing because some hydrogen gas also, the hydrogen gas is going to be produced. Then that thing, the manganese for oxide oxidizes it also. But now when I have that polar spot and the zinc rod, when I place them into the gas jar, it is going to contain a solution of ammonium chloride. Now, what are the limitations of the large wet cell now at that point? It means, we talk about the limitation of the large wet cell, it means now at this point, that when we talk about the limitation, the thing that we limit it, that does not exceed, like here when we look at it. Now, you see that it is depolarizing action is very slow. That's one limitation that we have it at that point. So what happens if the depolarizing action is very slow? It means now at that point that that cell is not suitable for maintaining a steady current for a long time. Once the depolarizing action is very slow, now our depolarizing action is that carbon, the mixture of powdered carbon and manganese for oxide. It is very slow. It means that cell is unable to supply current for a long period of time because of that thing. So this limitation, you just say that the depolarizing action is slow. Therefore, the cell is unable to maintain or to keep current for a steady period of time, for a long period of time. It is not able to do that. Now, how can I maintain the large wet cell? Now, the large cell, to maintain it is, remember it keeps on, it keeps on evaporation. Now, at that point, we keep on adding water, we keep on pouring water in that large cell. If I want to maintain it such that it can continue working, so which means we say that you add water to make up it for the losses due to evaporation, because this cell will keep on losing. When at time to come, electrons keeps on losing the electrons now at that point. Now, when those electrons are lost, which means some at that point, when electrons are lost, we expected the manganese oxide to oxidize the hydrogen gas to form the water. But now that thing is not going to be working because it was evaporating. But now we keep on adding water, because water is the one which was helping us, helping that cell to supply the current now at that point. So to maintain it, we keep on adding water on it to cater for the losses due to evaporation, the loss of electrons due to evaporation. That's the way we can maintain at that point. Are we together? Now we are going to stop here, but then next time we shall start with the secondary sets. But in case you have a question, we can use this time for harmonizing. Those ones that have questions to ask.
Yes, teacher. There, right now I can see 2 people. I don't know if more will come, but let's start with these ones and see what they have for you.
Yes.
Linda, please unmute.
Good afternoon, sir.
Good afternoon to you.
Good afternoon, sir.
Good afternoon to you.
Yeah, however, the natural cell, the one is in welding.
I have not got you. You try to get some clear network.
Okay.
Then, yes.
Okay.
Anyone who has heard her question can
Teacher,
re-echo it.
she's not
Okay,
so
it's
clear.
like this. Like, how does the Lanchi wet cell look like? Okay.
It
Like,
looks like
it's
a dry cell.
Hey.
The difference between a Lanchi wet cell and a dry cell is it's only the electrolytes that differ, but the rest of the things, they are the same. So if you want a Lanchi wet cell, where you have the electrolyte as ammonium chloride jelly, you put the liquid ammonium chloride solution. That is the only difference thing. In case you're drawing.
And sir, okay, sir. And another question, is there a difference between an electrolyte and a electrolyte? Electrode, no? Is it electrode?
Yes.
Yeah,
yes,
electrode and electrolyte.
There is a difference between an electrode and an electrolyte.
Hey.
Electrode, in just in a simple terms, remember when we talked about the zinc, when I talk about the zinc plate and the copper plate, those metals are what we call the electrodes. That's why you can say negative electrode and a positive electrode, right? Those are the electrodes that we have at that point, those plates. And like where we have the cathode and anode. Though whenever I have, for example, when we draw it in this, when I draw something like this and this, these are now electrodes that I have. I can have maybe zinc here, then copper here. These are electrodes that we have at that point. Now, when I talk about an electrolyte, now, which means these electrodes, now when talk about this is where we have the anode and the cathode, which means we have the loss or gain of the electrons at that point. Those are the electrodes. Now for electrolyte is when I'm now going to dump I am going to drop deepening these electrodes into the electrolytes. Maybe I put my electrolytes like this. Now I've dipped the electrodes into the electrolyte. What is the work of that electrolyte? Which means this is where it is going to make these electrodes to be reactive now at that point. That's just the work of the electrolytes to help them to become more reactive. Yeah, so there's a difference between electrode and electrolyte. You get it?
Yes, sir. Sir, another question about the repetition. I want the repetition for this question. Why the electromotive force of a dry cell decreases with time when not in use?
Now, for that one,
Yeah.
with time, you find that the anode loses because electrons move from the anode to the cathode. The anode loses the electrons. When it loses the electrons, it means the ammonium chloride jelly will be unable to supply. Now it's not able to supply the current, hence that made the EMF reduces at that point. That's why I have it at this point. When we're explaining at first at this point, that the anode loses almost all its electrons, and the electrolyte, which is ammonium chloride gel, is unable to supply current anymore, and the reaction keeps on reducing, hence EMF decreases. You get it?
Yes, sir.
Yes.
Thank you,
We
sir.
shall share the notes to the group. You're all going to get these notes from the group. The last person as we are winding up because we have only 2 minutes.
Okay, the last person I'm going to pick is Trevor. Trevor, please unmute.
Okay, fine, thanks. So my question is a simple cell an example of a galvanic cell?
A galli?
Hello?
Yes, I'm getting you.
Galvanic is a simple cell an example of a galvanic cell? Because literally they say that the anode is a positive and the cathode is the negative, and unless in the case of the galvanic cell, where the cathode is the positive and where the anode is the negative. So
Yes.
that was my question. Is it an example of a galvanic cell?
Now, when talk about a galvanic cell, when we looked at first in this type of cells that we had at this point, let me first get them. We had these cells that we had these cells, 2 of them that we are having at this point. So you find that for a galvanic cell, we are going to look at it in front. It is in front of this notes. We shall look at it and we get at that point. Now, when you talk about the cathode being negatively charged and anode being the positively charged, before I explain anything, what do you mean first of all from there that some cells have the cathode being negatively charged, then some having the anode being positively charged?
Okay, here they're trying to tell me that the cathode, where I'm reading from, the cathode is an electrode where a reduction occurs. This is a common chemical. This is common in an electrochemical cell, where the cathode is the negative, as the electrical energy that is supplied to the cells results in the composition of the chemical compound. However, it can be positive, as in the case of the galvanic cell, where the chemical reaction leads to generation of electrical energy. Yeah.
Now when you go deep
and also
in
And also in other applications like electronics, where we find the lead, the anode is the positive and the cathode is the negative. So particularly that's where like I knew the context, but in the simple cells, it somehow changed and I was wondering what makes it change and like
Yes,
that.
right now when we are dealing with these cells, we are dealing with those. When you go deep in a electrolysis, when like in chemistry, you learn deep about them, right?
Okay.
But in physics, we pick what is so much applicable that can help us to generate current, that can help us to solve the community problem. So that's why we don't go deep in electrolysis or electrochemical cells as you go in chemistry. You're going to learn more, and you find that most students keep on confusing things now when they come to this topic from here. So here, when talk about it, first consider that we are focusing mostly in that galvanoic cells where we talk about it. Don't first bring that the cathode is negatively charged, the anode is positively charged. First leave it. When reaching in front, we can explain. I don't want you to first confuse people right now. When we go to the next lesson, then we can go and talk about those ones. I was just requesting you. Let us not first confuse people to change anything right now. Are we together?
Okay, thanks.
Then the next lesson, we shall explain now more about it.
Okay.
Yes. So as we are winding, let me call Mr. John to come and close.
Okay, friends, we can stop here. We shall start from here another time. A closing prayer, someone to give us a closing prayer.
Teacher.
Yes.
Many hands are up, but I'm going to pick one to give us that closing prayer. Let me go with
Yes.
Patricia. No, I'm saying many hands are up, so I'm picking one to give us a closing prayer.
Let's humble ourselves and pray. Dear Heavenly Father, we're so grateful to you for this lesson. Thank you for the far we have come. Thank you, Father, for enabling us finish it. Thank you, Father, for where we have understood and where we have not understood. We pray, oh Father, that as we go back, may we please revise what we have learned and may it sink down into our minds. King of Glory, I pray for our teacher. Thank you so much for guiding him, for giving him the grace to teach. May you bless him and his family. Bless all our teachers who are here present with us. And we pray, oh Father, that even as we go right now, may you anoint us with your hand of healing, and may your protection be upon each and every one. We have prayed less, but expecting more from you. And above all, Lord, may your will be done. In Jesus' name I've prayed and believed. Amen.
Amen. Amen.
Thank you so much.
Have a lovely evening.
You too, sir.
Bye, everyone.
Bro man, you're in Amabina. You know, you're posting of Are you being paid?